So last week, we were talking about how exponential functions are really similar to those geometric sequences we saw in our last unit. You guys can see on page 5, but I'm going to flip back to the beginning of our packet. The first couple of examples that we looked at, we said we had those two purses. Remember, we said purse A looked a lot like an arithmetic sequence and purse B looked a lot like a geometric sequence. But then we talked about how really I could also say that that arithmetic sequence was a linear function. And that thing that we called a geometric sequence, I could also relate to it as an exponential function. Okay? And so we plugged some values into each of those formulas. And we were looking at how the sequences we had just talked about actually related a lot to functions. And then the next thing that we talked about, this would have been Thursday of last week, were a couple more examples of sort of patterns I could describe as arithmetic sequences or linear functions. Little difference in notation there, but the big idea was the same. The biggest difference between the two was that for a sequence, I would have just the values listed in our table, but for a linear function, I would get everything in between. And then we said the same thing for another example that looks like a geometric pattern, a geometric sequence. But if I thought of it as an exponential function, I would get those values in the table, but all the ones in between as well. Okay, and again, we looked at if I evaluate for a term in a sequence or a value of our function, that works essentially the same way. So what we're going to look at today is, again, this idea that an exponential function can model information for me, can model these patterns that look like geometric sequences, and we called geometric sequences in our last unit. But today we're going to really shift into that function idea, okay? So we're not going to call anything a sequence today. We're really going to stay in function land. So on page 5, our first example for today says we have a marine biologist that estimates the structure of coral has a volume of 1,200 cubic centimeters, and then that volume doubles each year. We're going to write an equation. We've got sort of a generic exponential formula here that represents the relationship where T is the time in years since the coral was measured, and Y is the volume of coral in cubic centimeters. So this looks just a tiny bit different than our function we worked with and our sequence formula that we worked with in our last unit. Before, we had a little -1 here. And there's a reason we had a -1 there. When we were looking at our sequence, and then even when we started writing those geometric or those exponential equations in this unit, we said that our sort of general pattern was that first term multiplied by whatever that rate of growth was to some sort of exponent. We used n-1 generally. The reason that we usually used n-1 was because from our sequences, we had the first term in a sequence or the second term or the third term. We had some term in our sequence. And that sequence always started with a first term, right? Or we had a second term or a third term, so on and so on. But when we talk about a function and having x and y values, I could actually have a value of x that's 0. And then whatever my corresponding y value is. So that's what we're looking at here. So instead of first term, we're going to just modify this slightly to be, for today, our initial term. We're going to see a lot of examples that talk about an initial measurement, or we first, for example here, we first measured the volume of our coral and found it to be this. So we're going to call that our sort of 0x, which means that if I'm using this y value, I would need to adjust from a 1 to a 0 here. Now, -0, if we're making that adjustment, -0 doesn't change that exponent at all. So if I plug in 2 here, it's going to be 2. When it was -1, that was important to have because 2 minus 1 is different than 2. So for today, that's why we're seeing that little change there, okay? Because we would just be subtracting 0 in our exponent. So if we take a look at number 1, again, we want to write this function here. We need our initial amount, our initial value. That's going to be our first measurement here of our coral, our first volume. So this would be y equals 1200 times how we're growing. Now this says that we double each year. What am I multiplying by if we double each year? 2. We're multiplying by 2. And then this says use t for my exponent because we're talking about time. If you use x instead, that's fine, but I'm going to use t here. So this will tell me how many times I want to multiply by 2. So there's my function representing the volume of my coral for however many years since my first measurement. Questions for me on number 1? Okay, so then number 2 is asking us to do something we've done before. Find the volume of the coral for the following values of t. So that means I'm just going to plug in t equals 0 to my function. Or I'm going to plug in t equals 1 to my function and figure out what I get. So you're going to want your calculators for this one. If you're using your TI Inspires, they recognize order of operations. So you can type this in exactly as it is. If you are not currently in the habit of bringing your calculator every day, you need to reform that habit because we're going to need them. If you're not using a TI Inspire, then remember that you are going to have to take care of order operations. So you're going to have to do the exponent first and then multiply by 1200. 2 to the 0 would just be 1. 1 times 1200 would be 1200. And then since this problem has a context, I'm going to go ahead and put the label on here. So we want cubic centimeters as our label. CM cube. 2 to the first would be 2 times 1200 would be 2400 cubic centimeters. 2 squared is 4 times 1200 would be 4800 cubic centimeters. And then 2 cubed is 8 times 1200 would be 9600 cubic centimeters. Anybody not get these? You had this same setup, but you got different answers? Okay. If at any point you do have the same setup that I do, but a different final answer, let me know. It likely means that we've just mistyped something in our calculators, or maybe we need to make sure we followed order of operations. It's almost always a simple fix, but I want you to make sure that you talk to me and ask that question so we can make that simple fix, so that you don't miss questions on a quick check or a quiz or a. Okay, So we know that our answer that we get out, that Y value, is cubic centimeters, right? It's giving me the volume of my coral. But what does the T number represent? Like we got 96 cubic centimeters here, but what does the 3 mean? Yeah, that means 3 years. 3 years after our initial measurement. So if we hop down to number 3 here, it says, what does it mean in this situation when T is -1? Yeah, is there another way that we could maybe phrase that? So this would be 3 years in the future, right? So this would be 1 year in the past. Yeah, I want to phrase it as we're losing a year. It's not like daylight savings, right? But yeah, this means a year before, right? Or a year ago, a year before we started our measuring. So T equals -1 would be the year before the initial measurement. Whenever that we took that initial measurement, this would be the year before. So what I want you to do now is actually find the volume in the past. So take our same function, 1200 times 2 to the something, and plug in these new values for T there. Tell me what we get. When T is -1, what's the volume for our coral? 600 cubic centimeters. Good. What about when T is -2? 300. And what about when T is -3? 150. Now, these values should make sense. We learned in the setup for our problem that that volume is doubling each year. So from 3 years ago when I had 150 to 2 years ago to when I had 300, that doubled, right? 150 times 2 is 300. And then between another 2 years, 300 to 600, I doubled again. From 1 year before to the year I took the measurement, I doubled again. And then for 1 year in the future, I doubled again. For 2 years in the future, I doubled again. Okay, those values should make sense based on what we know about that sort of rate of growth. Questions for me on page 5? Okay, we're going to take a look at a couple more examples for today. If you would, please turn the page. And on page 6, this time they've given us the function to start. This is a forest fire has been burning for several days. The burned area in acres is given by this equation, where D is the number of days since the area was first measured. Complete the table below. Now we wrote the equation last time. This time they've given it to us. So we can see that initial measurement, that initial amount, and then we can see our growth or our change, might be a good way to put this. So in this table here, we want to do exactly the same thing. We've got some values that we're going to plug in for D. our sort of initial value here, days since we measured, is 0. So that would be the day that we took the measurement. The day that we took the measurement was 4,800 acres of burned land. So now you're going to do the same thing we just did. This time it's just organized in a table. Okay, so you've got values for D here that I want you to plug in and tell me what you get. What do we get for Y when D is 1? Good. When D is 2, 19,200. When D is -1, 2,400. And when D is -2, 1,200. Good. Interpret your answer for D equals -2. What does it mean in the context of the problem? Well, what does the -2 represent? 2 days before the initial measurement, 2 days before the initial measurement, what does the 1,200 represent? Yeah, so this represents our time in days, and this represents our acres burned. So 2 days before the initial measurement, 1,200 acres had been burned. 2 days before the initial measurement, 1,200 acres had been burned. Very good. Questions on that first problem? Okay, now let's take a look at the second problem. It says the value of a home in 2015 was $400,000. Its value has been doubling each decade since. So we have our initial measurement there, and then we have a description of how we're changing. We're doubling each decade. So the first thing we want to do, it says if V is the value of the home in dollars, write an equation for V in terms of D, the number of decades since 2015. So that it's easy to get sort of lost in the details here, but the key thing is that we want to write an equation for this guy. Okay. Now it's saying use V to represent the value of the home and use D to represent the decades that have passed, since that's sort of the time frame that our value is changing on. If you use X and Y on this one, that's fine too. I'm going to use V and D since that's described in our problem here. But our value would be equal to that initial amount that we had, 400,000, times, we're doubling. So what are we multiplying by when we double? 2. And then it says use D for our decade. So D would be our exponent for 2. Now that we've written our function, it's asking us to evaluate our function at some different values for D and then explain what that means. So for B, it says, what is V when V is -1? So that would be 400,000 times 2 to the -1st. So if we evaluate that, again, you would want to use your calculator here. we would find a value of $200,000. This means, in the context of our problem, that 1 decade before, remember we're working in decades for this one, -1 would be 1 decade before. 1 decade before 2015, because that's when we took our initial measurement. But you could say 1 decade ago, or you could say in 2005, since that would be 1 decade before 2015. 1 decade before 2015, the home value was $200,000. For C, what is V when D is -3? Same idea. 400,000 times 2 to the -3rd power would give us a value of, what's our value here? 50,000. Good. So this would mean, since it's negative, 3 decades before. 3 decades before 2015, or 3 decades ago, or 1985, if you do that math. 3 decades before 2015, the home value was $50,000. Now you try the last one. Give me that value for when D is 1 and give me an explanation. What's V equal to for part D? $800,000. What does this mean in terms of the context of our problem? Yeah, 1 decade after 2015, or in 2025, the home value is $800,000, or will be $800,000. Now, I want to take a second to point out that everything that we've looked at here, we've done before. Okay, so we've plugged in values to our function, values for x. We've also interpreted a value for x, in this case d, as well as a y value in the context of a problem. We did all of these things with linear functions last semester. The only difference is that now we're looking at exponential functions. So our new thing here was writing those exponential functions, which we worked on last week. But where we already had the function, nothing that we did for this problem is something that we haven't done before, okay? All the same stuff that we've worked on, just with a different type of function. Questions for me for today? Okay, perfect.